Now that we've looked at some general properties of discrete distributions, we can focus on some particular patterns that occur in lots of different areas. And the first of these is the binomial distribution. And this is when you do an experiment which has got two possible outcomes, that's the bi in binomial, and you repeat the experiment many times. You might toss a coin 50 times, heads or tails. You might toss a drawing pin 100 times, pin up or pin on the surface, and so on. Whenever there's two possible outcomes, each time you do the experiment, the probability of a success is the same. And we use the word success or fail, although we might not really think of it as having any particular value. So we might say a head or a tail, or if I roll a die, I might get a 6 or not a 6. Two outcomes, so it's binomial, and the probabilities are the same each time we roll that die. They do not depend on what happened last time. There are more complicated situations called Markov processes, where what happens next time does depend on what happened before. If we think about weather, is it sunny or rainy? Well, that depends on what happened yesterday and then on the day before. But binomial, the probabilities are the same each time, and we do a fixed number of experiments. So let's, for example, toss a drawing pin 3 times. And let's suppose that the probability of getting a pin up is 1/4. That's that scenario. What are the probabilities of the different possible sets of outcomes? Well, we can analyse this with a tree diagram. The first toss of the drawing pin, we can have up or down, and that's 1/4, and that's 3/4. Then we can have the second throw. Again, it's 1/4, 3/4, 1/4, and 3/4. That's the second throw. Then I can have the third toss of the pin. And again, whatever had happened before, I can still get pin up or pin down. And again, it's going to be the same sequence of probabilities. The pin does not remember what it did before. We should always remember that, these inanimate objects, if you toss a coin 20 times, if it's a fair coin, even if you've got 20 heads in a row, it's still 50-50 next time. Coins do not remember. Drawing pins do not remember. Now we know how to work out the probabilities of the various patterns. The chance of getting 3 ups is 1/4 times 1/4 times 1/4. Which is 1 out of 64. The chance of 2 ups and a down is 1/4 times 1/4 times 3/4, which is 3/64, and so on. And there are 8 possible sequences. But what we're going to be interested in is how many different ways can, for example, 2 ups and 1 down occur. What is the total probability of getting up twice when I do the experiment 3 times? This was one way of getting a UUD. Another way of getting 2 U's is this sequence. 3/4 times 1/4 times 1/4, which is 3/64. That was a down followed by 2 U's. And in here, I missed it out, there's another one with 2 ups. If you get up, down, and then up, and that's 1/4 times 3/4, 3/64. And those are the 3 different ways in which we can get 2 ups and 1 down in 3 tosses of the drawing pin. And what we want to do is find a quick way of doing this calculation. This tells us, of course, that the probability of getting 2 ups is 3/64 plus 3/64 plus 3/64, because with tree diagrams we add alternative trails, so we get a total of 9/64. Now the idea of the binomial distribution is to try and put this into a simple form whereby we can work this out immediately without having to draw tree diagrams or do lots of repetitive calculations. So let's try and figure out what's happened and how we can generalise that. Let's now look at a case where we have an experiment. So we repeat an experiment n times, and the probability of a success equals p. So in this case that was a quarter and we did it 3 times. What's going to happen generally? Well, we can imagine what the tree diagram would look like. So the probability of x successes. How can I get x successes? Well, the successes might be the first couple. So when I was chasing ups, I could have my 2 ups and then the fail. And the chance of that is the chance of the first success, which is p, times p. And I will keep doing this, x times p times p times p. I want a success and another success and another success. I keep doing that, x times. And the remaining experiments, in this case there was 1 left. We wanted 2 ups, so there was 1 down. That came at the end with its probability, and that probability is 1 minus the original. So what I now need is the chance of getting a fail and another fail. And if there are n experiments altogether, in this case 3, if there were 2 successes, it was 3 minus 2 fails, which is 1. In this case, I will want n minus x fails. That's the probability of one particular trail through the tree diagram. But what we now have to do is see how many different trails would all give the same final outcome, in this case 2 ups. So we have to multiply this by the number of different ways that you can get x successes in n experiments. And for the moment I'll just put a formula here, or a label. It's called n choose x, and that's called the binomial coefficient. And we work this out, and sometimes it's written as a bracket. Looks a bit like a vector, nx. And this formula involves factorial numbers. N factorial over x factorial times n minus x factorial. Now factorial n is that number times the next one down, times the next one down to 1. So that tells you how many different branches in the tree diagram would all represent the same final outcome, 2 ups out of 3. We're not bothered about the order where these successes occur. We just want to get the right number of successes. So let's see how this works out in our case. Going back here, we'd have p to the power x. Well, let's first of all summarise this. P to the x, 1 minus p to the n minus x times n choose x. That's the binomial formula for working out the probability of getting x successes in n experiments. So in our case, p was a quarter, and we wanted 2 successes out of 3. 1 minus p, 1 minus a quarter is 3/4, and we wanted 3 minus 2, which is 1 fail, and then we wanted 3 C2. Often we say 3 choose 2, and that's 3 factorial over 2 factorial, and then 3 minus 2 is 1 factorial. So a quarter squared is a 16th, 3/4 to the 1 is 3/4, And then 3 factorial is 3 times 2 times 1, which is 6. 2 factorial is 2 times 1, and 1 factorial is 1. And so we can see that this is going to give us 3. It's the 3 different ways in which we could get this particular outcome. So if I multiply this all together, I get back to 9/64 as before. So that's the formula for the binomial distribution.
Okay, Mary, so let's have a look at this one. So solve x plus 2x equals 12. So what do you think you do first?
Okay, well, I want x on its own, so I would put x equals 12 minus 2x.
Okay, so a lot of the time we want to get x by itself, but what we want to do first is get all of these x's together. So can you see anything we can do with this? Get all these together in one place.
Oh, okay, it's 3x, isn't it?
Yeah,
so
absolutely.
3x equals 12. Oh, and so x equals 4.
Brilliant, spot on, well done.